So good afternoon, everyone. I hope you're having a good afternoon. So my presentation is regarding the remote sensing application in forestry, precision forestry. So my presentation is entitled Inventory Predictions Using Radar, LIDAR, and Satellite Data. We might all agree that forest owners and forest managers require detailed, current, and reliable information to predict forest inventory. So this is reasons behind this involves monitoring crop health and damage, optimizing silvicultural treatments, and establishing stand volume and value. How do we do this? There are different methods on how we do this. The first part is sample-based methods, which is field measurements, and is usually laborious, costly, and very time-consuming. So luckily, we also have remote sensing technology now, and with our range of sensors, range of platforms, we can deliver information in broad scale and in a regular manner. So when we talk about remote sensing, especially in forest inventory prediction, we are usually talking about elevation and height metrics. So just a recap, and so we're all on the same base. This figure illustrates a sample vegetation surface on a terrain, and when we talk about the elevation metric that includes the objects on the surface, we're talking about the digital surface model, or DSM. And when we are talking about the digital terrain model, this is the bare earth model with the terrain features, such as ridges and valleys. So when we try to normalize our terrain and get the height of the objects on our surface, we can get the canopy height model, or CHM. These types of information can be gathered through different remote sensing datasets and remote sensing sensors. So the most common one is LIDAR data, or airborne laser scanning systems. So when we say common, LIDAR is actually operational in different countries. So in terms of accuracy, it is known as the most accurate sources of terrain and elevation models. So it is a source for characterizing biophysical variables and forest properties in different levels, such as stand level, plot level, and tree level. So this gives us three-dimensional view of our forest, and up or down to the underlying terrain. And countries that have national LIDAR datasets inventory are Canada, Switzerland, and Finland, and many others. And in New Zealand, I think LINS is starting this effort, and high accuracy LIDAR datasets is available for different parts of the country. One drawback of using LIDAR is its expensive nature. So application is therefore limited to local scales because it is expensive, and there's this complicated logistics in flying because these sensors are oftentimes on board airborne vehicles or UAVs or drones. So when we have LIDAR data, we can derive information that I mentioned earlier, such as DTM, DSM, and CHM. We can derive height at different percentiles, since this is 3D information that is available, and other metrics such as statistical metrics of height, mean, standard deviation, skew, kurtosis, and others. So an alternative to LIDAR, there are different alternatives to LIDAR, and I will discuss two of them, and both are satellite-based remote sensing techniques. So the first one is radar, and when I say radar, I am particularly talking about synthetic aperture radar. It is relatively low cost, which is very important, and data can be gathered through a broad spatial scale. It is an active sensor that operates in the microwave region. This means that data capture is available even if it's even during cloudy season and even during nighttime or daytime. So solar illumination and cloud is independent. And however, SAR has complicated data processing, and because this is not usually used, high expertise is needed, and it is known to have relatively lower resolution and accuracy compared to LIDAR. However, SAR is being used to model forest inventory in European and tropical forests. Using SAR data, we can derive also DSM, DTM, and CHM. This is not 3D information, so we can't derive height at different percentiles, but we still have SAR observables, which can be independent of height. For example, we have the roughness and smoothness of our surface. So the second one is point cloud data. And this is derived using satellite stereo imagery, which has very high spatial resolution, and through photogrammetry, point clouds can be generated. So this is still relatively low cost compared to LIDAR, which is, by the way, 3 to 5 New Zealand dollars per hectare. But like SAR, it cannot be used for vertical characterizations. And since this is a passive way of remote sensing, it is limited to cloud-free conditions and daytime acquisitions. We have DSM with satellite point cloud datasets, and we can derive CHM, but we have to outsource our DTM. We don't have height at different percentiles, though we can derive heights at relatively high percentiles, but not the lower ones. And we can also have other metrics, such as the statistics of height. So what we wanted to do is to compare the model precision for 4 forest inventory attributes using metrics from LIDAR, SAR, and satellite satellite point cloud data for simplicity. So our 4 attributes that we're trying to predict are mean top height, basal area, stand density, and total stem volume. So our study area is the Geraldine Forest in South Island. It consists mainly of radiata pine. It is a very complex 60 square meter forest. So its terrain varies from 145 to about 860 meters. And the slopes are rolling to steep from about 0.04 degrees up to 67 degrees, which makes it a very complex study area. So this is a summary of the remote sensing datasets that we used. Just to point out the key important data, the sensors are, only the LIDAR sensor is on board an aircraft or a drone, and the other ones are from satellite vehicles. So also the date of capture for the field data that we are comparing these remote sensing data sets are captured on June 2016. And the yield is predicted backwards using a forest yield prediction software package to match the 2014 data that we have for SAR. And also, it is important to note that we have varying spatial resolutions from 1 meter for LIDAR, 2 meters for satellite point cloud data, up to 5 to 10 meters for SAR data. A general overview of our methodology includes the three remote sensing data sets that we have and how we compare it with the field data. And this groups of data sets are used as an input to models. So we used random forest regression model for SAR. It is an ensemble of large decision trees, while the elastic net regression model was used for the satellite point cloud. So this is a regularized regression model that penalizes complexity. So our predicted variables are the 4 ones. So that's the output, the main output of the models. So key results, we tried to compare LIDAR DTM with the SAR DTM, and we noticed a very high correlation between the two DTM parameters. However, our RMSE value, or root mean square error value, is 8.1, which can be significant in most cases. And also, we noted that the error is higher for steeper slopes and is lesser for flatter areas. So it is the same for the LIDAR DSM and SAR DSM. It's very highly and positively correlated, but the RMSE of 4.6 is significant. It can be significant in most cases. So the map on top is a CHM map derived from LIDAR, and in comparison, the SAR CHM has a low correlation with the LIDAR CHM. So this is where the errors from the DTM and DSM portray. So this low correlation is due to the errors propagated from the previous metrics. So what we tried to do is use the LIDAR DTM and SAR DSM to produce a mixed CHM, which has a relatively, which increased the correlation significantly. As for the CHM for our satellite point cloud data, so those maps show the difference in resolution and difference in detail that you will see when you decrease your resolution from 1 meter to 2 meters. And the LIDAR, we also present the LIDAR height versus the satellite point cloud height at 99%, at the 99th percentile, which is still relatively strong, which with an R² of 0.62. So both of the LIDAR CHM and satellite point cloud CHM at percentiles from 90 to 99 has relatively good correlations with mean top height, as seen in the R² table. So looking at the models side by side, we try to compare the LIDAR versus PCD versus SAR and their precision when predicting mean top height, basal area, stand density, and total stem volume. So regardless of the model used, the attribute with the highest predictions or highest precisions of the model is the mean top height, followed by the total stem volume, followed by basal area, and then stand density. So this is regardless if you use LIDAR, satellite, point cloud, or SAR. And also, regardless of the attribute that we are predicting, LIDAR performs better than satellite point cloud data, and both performed better than SAR. So we can see that in this certain type of study area, which is a very complex forest, SAR doesn't perform well, but we can see that satellite point cloud data might be a viable alternative to LIDAR data. So looking at the same models but with different metrics, so this time error expressed as a percentage of the mean, we can see the same, essentially the same precision per attribute and precision per sensor, but we can note things like the expected error for LIDAR is 5.67, but if for mean top height, for an instance, but if you use satellite point cloud data, that error might increase with about 1%, but that error might double when you use SAR. So these types of information are important when you're deciding which remote sensing data is best used. So to summarize, in terms of accuracy, LIDAR no doubt performs better than satellite point cloud data and SAR. For example, to model a mean top height in a complex forest like Geraldine Forest, you're expecting your R-squared values to be 0.86 for LIDAR, 0.81 for satellite point cloud, and 0.60 for SAR. However, we should take note that, again, our study area is a very complex forest, and this SAR datasets or SAR performance can be improved. This can be improved through further data processing or even alterations within your data acquisitions. And also, this has been shown in other studies, such as in Sweden. Their forests performs better with R-squared of 0.9 and errors less than 5%. So these are relatively flatter areas. And also, we shouldn't forget that SAR still has its advantages, being an active remote sensing sensor. It can capture data even with cloudy areas, even in cloudy areas, and even in nighttime and daytime. For the satellite point cloud data, even though it performs slightly worse than the LIDAR data, it is still fairly accurate, and it just needs a precise DTM it just needs a precise terrain model, which can be beneficial because this is being the LIDAR data set within New Zealand is being captured with LINS. So in terms of cost, SAR is less expensive than satellite point cloud data, and and the two are less expensive than LIDAR data. So approximately, the cost of the data capture per hectare are 16 cents for SAR, 40 to 85 cents for satellite point cloud data, and $3 to $4 for LIDAR. And also, we have to take note that this costs are estimated during the time of the study, and this has minimum order requirements. So with cost and accuracy and going beyond that, we still have to consider many other things, like what are the parameters that are being predicted, what is the nature of the forest, which is our study area, is it in the steep terrain, is it homogeneous, and how remote or scattered is our resource, and thus the sampled area suffer from persistent cloud cover, and are we requiring just one-time capture or regular monitoring of our study area? So we further recommend that forest managers should take all factors into consideration when deciding which best remote sensing datasets and technologies to use. High precision, if we require high precision, we should always resort to LIDAR, and in case when LIDAR is very costly to acquire, satellite point cloud data and radar are always there, especially when your area is area is wide and your resource is scattered. And if there is persistent cloud cover but in a relatively flat area, you might consider radar. And also if high precision is not required. And there are still gaps for future research to examine the precision of radar on flat terrain. also using a more optimized capture specifications. This study was funded by the GCFF and New Zealand Forest Growers Levy Trust. We would like to thank LINS for the additional support for the ALS data capture, and Aaron Gunn and Port Blakely for providing access to the forest and associated inventory data. So that concludes my presentation. Thank you for your attention.